Welcome to G Fun Facts Online. Today we are bypassing the traditional introduction and diving straight into the physical limits of artificial intelligence and the radical engineering marvel that is actively shattering those limits. We live in an era where artificial intelligence is fundamentally defined by computational hunger. As the global economy pivots aggressively toward AI-driven automation, accelerated scientific discovery, and real-time generative models, the underlying hardware powering these revolutionary systems is hitting a massive physical and architectural wall. For the past few years, we have successfully scaled our models to hundreds of billions and even trillions of parameters. Yet, despite this algorithmic triumph, we find ourselves physically trapped by the speed at which we can move data. In the high-stakes multi-billion-dollar race toward artificial general intelligence, or AGI, the dominant bottleneck is no longer simply raw compute capability. We have processors that can do the math. The real enemy now is latency. The microsecond delays incurred when shuffling data back and forth between memory chips and compute processors, multiplied across massive clusters of discrete chips in a data center, accumulate into an insurmountable barrier known in computer science as the memory wall. To understand the solution, we must first dissect the problem. For over a decade, the graphics processing unit, or GPU, has been the undisputed workhorse of the AI revolution. Originally designed to render millions of polygons for video games, GPUs rely on massive parallel processing. This made them fortuitously well-suited for the matrix multiplications required by deep learning neural networks. However, GPUs were never explicitly built from the ground up for artificial intelligence. They were adapted for it. As AI models have grown exponentially, scaling at a rate 25,000 times faster than Moore's law at its historical peak, the fundamental architecture of the GPU has begun to show severe strain. Modern AI workloads, particularly large language models, like those powering advanced generative AI, are not compute-bound, they are memory bandwidth-bound. When an AI model generates a response, it undergoes a process called inference. During text generation, the model predicts the next token, which is a chunk of a word, based on the preceding context. This operation relies heavily on something called general matrix vector multiplication. In this operation, the entire weight of the neural network, which can be hundreds of gigabytes in size for a frontier model, must be streamed through the compute cores just to generate a single token. Because traditional GPUs have very limited on-chip memory, typically around 50 to 100 megabytes of ultra-fast static RAM, the vast majority of the model's parameters must be stored in external high-bandwidth memory. The processor itself is remarkably fast, but it is constantly starved for data. It must wait for the neural network parameters to travel from the external memory, across the chip's physical interfaces, and into the compute cores. This journey, though measured in nanoseconds, is an absolute eternity in the realm of computing. The compute cores sit idle, burning massive amounts of power while waiting for data to arrive. This exact phenomenon is the memory wall. To mitigate the fact that a single GPU cannot possibly hold a massive trillion-parameter language model, engineers are forced to cluster thousands of GPUs together. Models are sliced up and partitioned using incredibly complex software techniques like pipeline parallelism and tensor parallelism. However, this introduces an even more severe latency penalty: interconnect overhead. When GPU A needs to send intermediate calculation data to GPU B, the data must leave the processor, travel through the external memory, traverse a high-speed external cable interconnect, pass through network switches, and finally arrive at the destination. No matter how incredibly fast these interconnects become, they are absolutely subject to the unyielding laws of physics. Moving electrons over copper cables, or even photons over fiber optic links across a massive data center, introduces unavoidable latency. In a distributed cluster, the system is only ever as fast as its slowest link. Amdahl's law dictates that the communication overhead eventually cancels out the benefits of adding more processors to the cluster. The result is skyrocketing power consumption, rapidly diminishing returns on performance, and an agonizingly complex software stack required just to keep the thousands of processors synchronized. Enter Wafer-Scale Computing. If the core problem is the physical distance data must travel between memory and compute, and between discrete chips in a sprawling cluster, the most logical and radical solution is to entirely eliminate the distance. In traditional semiconductor manufacturing, a large silicon wafer typically about 30 inches or 300 millimeters in diameter, is etched with hundreds of identical chip designs. The wafer is then physically cut or diced into individual chips, which are packaged separately. This has been the standard for decades because microscopic defects are mathematically inevitable in silicon fabrication. A single microscopic dust particle can completely ruin a transistor. By cutting the wafer into hundreds of small chips, manufacturers can simply throw away the defective ones and keep the working ones, ensuring a profitable yield. Wafer-scale computing throws this conventional wisdom completely out the window. Instead of cutting the wafer into hundreds of small, disconnected chips, the entire dinner plate-sized wafer is kept intact and permanently wired together to act as one colossal, monstrous, unified processor. The most prominent pioneer and master of this technology is Cerebras Systems. Their flagship processor, the Wafer-Scale Engine, represents an absolute masterclass in extreme engineering and serves as the definitive counter-architecture to traditional GPU clusters. To truly grasp the magnitude of wafer-scale computing, one must look closely at the specifications of the Cerebras WSE3, the third generation of this revolutionary architecture launched specifically to tackle the most demanding AI workloads in the world. Manufactured on a cutting-edge TSMC 5nm process, the WSE3 is a physical monolith. It boasts a size of 225 square millimeters. It is roughly the size of a dinner plate, making it an astonishing 56 times larger than the largest GPU currently on the market. It contains 4 trillion transistors. To put this mind-boggling number into perspective, a cutting-edge GPU houses around 208 billion transistors. The WSE3 has nearly 20 times more. Across this massive silicon canvas, there are 900,000 AI-optimized compute cores. These cores are entirely unburdened by legacy graphics hardware. They are pure AI calculating engines built specifically for sparse tensor operations. But here is the critical differentiator. The WSE3 holds 44 gigabytes of ultra-fast static RAM directly on the silicon. While GPUs rely on external memory, this entire 44 gigabytes is just one single clock cycle away from the compute cores. Because of this architectural layout, the memory bandwidth reaches an incomprehensible 21 petabytes per second, that is, 21,000 terabytes every single second. This represents a 7,000-fold increase in memory bandwidth compared to traditional GPUs, completely and utterly shattering the memory wall. It delivers a peak compute of 125 petaflops of AI performance on a single piece of silicon. Because the WSE3 keeps 44 gigabytes of high-speed memory strictly on chip, it can store the entirety of massive language models, or huge contiguous blocks of trillion-parameter models, directly next to the cores. There is no off-chip memory to wait for. There are no PCIe lanes to bottleneck the data. There are no copper NV-link cables adding latency. Everything occurs within a unified, uninterrupted silicon domain, allowing data to move literally at the speed of thought. For decades, the semiconductor industry viewed wafer-scale integration as an impossible pipe dream. In the 1980s, ambitious companies like Trilogy Systems attempted to build wafer-scale chips, but failed catastrophically due to manufacturing yields and thermal issues. So how did modern engineers overcome the unforgiving laws of physics that doomed all previous attempts? The primary argument against wafer-scale chips has always been the yield problem. Statistically, a 12-inch silicon wafer will always have microscopic manufacturing flaws. If the entire wafer is treated as one chip, a single defect should theoretically ruin the entire multi-million-dollar piece of silicon. The brilliant solution lies in massive redundancy and a highly advanced routing architecture. The Wafer-Scale Engine is not one giant monolithic core. It is a meticulously engineered mesh of 900,000 independent compute cores connected by a high-speed fabric. During manufacturing, engineers intentionally build more than 900,000 cores on the wafer. Once fabricated, the wafer undergoes rigorous testing to identify exactly which cores contain physical defects. The system then utilizes internal routing logic, permanently baked into the hardware, to map around the dead cores. If a core needs to connect to another core, but the silicon directly between them is flawed, the fabric seamlessly and instantly routes the data through an adjacent, fully functioning path. This software-defined, hardware-enforced defect tolerance ensures that even with a normal distribution of manufacturing flaws, the wafer functions perfectly as a unified whole, maintaining a 100% yield for the usable product. Another major hurdle was scribe line routing. Traditionally, wafers have empty spaces called scribe lines between chip dies, where the mechanical saw cuts the wafer. To make a wafer-scale chip, engineers had to figure out how to transmit high-speed data across these scribe lines so the individual dies on the wafer could talk to each other. Cerebras developed proprietary interconnect technology that physically spans these scribe lines, seamlessly stitching the individual dies into a single, cohesive communications network. This die-to-die connection offers up to 10 times more bandwidth per unit area and a 100 to 300 times latency benefit compared to conventional printed circuit board interconnections. Then comes the issue of taming the immense heat and delivering power. A silicon chip, the size of a dinner plate, containing 4 trillion transistors, consumes a massive amount of electricity. The WSE3 system operates at roughly 23 kilowatts of power. Delivering 23 kilowatts of power uniformly across the surface of a fragile silicon wafer, and then extracting the resulting heat without physically cracking the silicon, is a monumental thermodynamic challenge. Traditional edge power delivery, where electricity is sent from the edges of the chip, is physically impossible at this extreme scale. The electrical current would drop off significantly before ever reaching the center of the wafer. Instead, power is delivered perpendicularly across the entire face of the wafer. To cool the system, the wafer is packaged in a highly specialized system that utilizes complex, aerospace-grade liquid cooling. A specialized cold plate circulates fluid directly above the silicon, drawing heat away uniformly. While this requires sophisticated water cooling infrastructure in the data center, it completely replaces the need for dozens of noisy, inefficient air-cooled racks in a traditional GPU cluster, dramatically reducing the overall data center footprint and total cost of ownership. The true validation of wafer-scale computing, however, is not found on a technical spec sheet. It is found in the physical reality of AI inference. In the rapidly evolving era of interactive and agentic AI, every single millisecond matters. A user waiting for a chatbot to generate a complex response, or an autonomous software agent waiting for a multi-step logic chain to resolve, is highly sensitive to latency. Traditional GPU clusters process language models at a rate of roughly 20 to 50 tokens per second for a single user. This is slightly faster than average human reading speed, which was acceptable for simple chatbots of the past. However, as the artificial intelligence industry evolves, this speed is no longer sufficient. We have firmly entered the era of reasoning models. Advanced models like OpenAI's O1, DeepSeek R1, and Alibaba's Qwen 3-32b do not simply spit out an immediate, unverified answer. They employ a technique called chain-of-thought reasoning. Before showing the human user a final answer, they internally generate hundreds or thousands of hidden thinking tokens, actively exploring multiple logic pathways, fact-checking themselves, and executing complex planning algorithms. If a reasoning model needs to generate 5,000 hidden tokens before finally providing an answer, a traditional GPU running at 50 tokens per second will force the user to sit and wait for nearly 2 full minutes. This crippling latency breaks the utility of AI in fast-paced enterprise environments, high-frequency trading algorithms, and real-time robotics. Because the Wafer-Scale Engine stores the model weights directly in its 44 gigabytes of on-chip static RAM and accesses them at an unbelievable 21 petabytes per second, it completely eradicates the memory bottleneck associated with matrix operations. The results are nothing short of staggering. On an open weights 70 billion parameter model, a Cerebras wafer-scale system can generate a verified 100 tokens per second. This is roughly 70 times faster than a traditional multi-million-dollar GPU cluster. For smaller models or specialized architectures, the speed can easily exceed 2,000 tokens per second, essentially delivering instant, real-time reasoning capabilities. When these reasoning models run on wafer-scale architecture, they can perform sophisticated multi-step logic and output a highly complex response in as little as 1.2 seconds, drastically outperforming the speed of top-tier models running on conventional hardware. This massive reduction in latency unlocks entirely new frontiers for AI. It enables instantaneous search, where AI search engines can actively synthesize dozens of web pages and generate a heavily cited response in the literal blink of an eye. It enables autonomous software engineering, where AI coding agents can write, test, compile, debug, and rewrite loops of code continuously without ever being stalled by inference latency. It also finally enables real-time voice interfaces, allowing AI voice agents to converse fluidly without the awkward 2-second processing pause that completely breaks the illusion of natural human interaction. Latency is not just a hardware problem, though. It actively creates a software nightmare. When training massive AI models, some of which are now nearing or exceeding 1 trillion parameters, the models vastly exceed the memory capacity of even a single wafer-scale chip. They must be trained across massive clusters of machines. In a traditional GPU cluster, distributing a massive neural network is an exercise in agonizing complexity. Because GPUs are connected by relatively slow network cables, software developers must carefully slice the neural network apart. They must use tensor parallelism to physically split layers across different GPUs, pipeline parallelism to split different layers across different servers, and data parallelism to copy the model to process different data batches simultaneously. The network traffic across the data center must be meticulously choreographed. If just one single GPU stalls or fails, the entire cluster sits idle, wasting hundreds of thousands of dollars in valuable compute time. Wafer-Scale Systems solve this massive headache through an elegant architecture known as weight streaming. Because the Wafer-Scale Engine is so massive and blindingly fast, it fundamentally changes the execution model of AI training. Instead of slicing the neural network into tiny fragments and scattering them across thousands of individual chips, the Wafer-Scale system keeps all of its massive compute cores entirely focused on the incoming data. The model weights are stored in central massively scalable external memory appliances that are capable of supporting up to 1.2 petabytes of memory. The weights are then streamed directly onto the wafer, layer by layer, in a continuous, uninterrupted flow. The entire wafer processes one single layer of the massive neural network at a time, instantly, before moving to the next. From a software developer's perspective, a massive cluster of wafer-scale chips looks and behaves exactly like a single gigantic processor. This concept of single-device simplicity means that AI researchers no longer need to spend months writing complex parallelization code. A scientist can define a massive 24 trillion parameter model with the exact same few lines of code used for a small model on a basic laptop. The hardware infrastructure handles the incredible scale automatically, dramatically accelerating the pace of AI research and massively lowering the barrier to entry for training frontier foundation models. While large language models currently dominate the mainstream headlines, wafer-scale computing is proving equally, if not more, transformative in the realm of high-performance computing and scientific research. The physical universe is governed by localized interactions. Whether a scientist is simulating the high-speed airflow over an airplane wing in computational fluid dynamics, analyzing the incredibly complex folding of a protein in molecular dynamics, or modeling the spread of heat through a new aerospace material, scientists rely heavily on solving partial differential equations. These real-world physical simulations are mathematically calculated using complex grid-based methods. In these computations, the state of a single grid cell is updated based entirely on the state of its immediate physical neighbors. This requires massive amounts of sparse, rapid communication between processors. On a traditional GPU cluster, moving this localized data back and forth across network cables creates a crippling latency bottleneck. A physics simulation can literally only run as fast as the physical network cables allow. The Wafer-Scale Engine's unique architecture, which is a spatially distributed mesh of cores with ultra-low latency interconnects and massive local memory, happens to be the absolute ideal physical substrate for physics simulations. Because every single core on the wafer can communicate with its direct neighbors in a single clock cycle, grid-based physics simulations map perfectly onto the physical silicon of the wafer. Wafer-scale systems have already achieved performance in scientific simulations that outpaces traditional, multi-billion-dollar supercomputers by orders of magnitude, turning what used to be months of simulation time into mere hours. This effectively enables high-fidelity digital twins, highly advanced material discovery, and vastly deeper, more accurate insights into global climate modeling. Of course, the transition to wafer-scale computing is not without its distinct challenges. The initial capital expenditure for a single system of this magnitude is immense, and the highly specialized liquid cooling infrastructure requires older data centers to fundamentally adapt their layouts. Furthermore, traditional programming paradigms still heavily dominate the industry. The vast majority of the world's AI code is currently written specifically for NVIDIA's CUDA software ecosystem. However, the sheer economics of latency and throughput are rapidly shifting the calculus of the entire industry. When evaluating AI hardware at an enterprise scale, the ultimate defining metric is the total cost of ownership per token generated or per model trained. Because a single wafer-scale system can functionally replace dozens or even hundreds of discrete GPUs, the overall system power draw, the cost of specialized networking equipment, and the physical floor space required are all drastically reduced. Moreover, in the critical realm of real-time inference, the historical lock-in of the CUDA ecosystem is virtually non-existent. Modern open-source frameworks seamlessly compile down to the wafer-scale hardware, allowing major companies to switch from traditional GPU clusters to wafer-scale inference with mere keystrokes. As AI inferencing transitions from a novel tech demonstration into the foundational, invisible layer of the entire global digital economy, raw efficiency per watt and tokens per second will undoubtedly become the defining metrics of the modern data center. Wafer-scale architecture provides a highly robust blueprint for how future exascale energy demands can be effectively managed through higher throughput and far more efficient data movement. Ultimately, the entire trajectory of artificial intelligence is governed by scale. Scaling laws consistently prove that larger models, fed with exponentially more data and vastly more compute, yield significantly greater intelligence. But as we aggressively push toward massive trillion-parameter architectures and highly advanced recursive self-improving reasoning models, the physical limitations of connecting discrete chips with copper wires and glass fibers become the primary obstacle to human progress. System-on-wafer integration is not just a neat trick. It is the logical, inevitable conclusion of the semiconductor industry's evolution. By fundamentally unifying compute processing, memory storage, and high-speed communication onto a singular, monolithic canvas, wafer-scale computing successfully eradicates the exact latency bottlenecks that have long plagued computer science. Through breathtaking engineering innovations like the Cerebras Wafer-Scale Engine, we are no longer building mere computer processors. We are constructing the foundational computational equivalent of a synthetic cerebral cortex. Massive, completely unified, and instantly interconnected, wafer-scale computing actively ensures that as the cognitive capabilities of artificial intelligence continue to rapidly expand, the underlying physical hardware will be ready to let it think at the speed of light.